Thank you very much, Emil. Thank you for the invitation and the kind introduction. So let me share. Right. I thought since there is a lot of discussions and debate about how really to integrate some new functionalities and some new goals when optimizing and designing the wireless systems of the future, I thought that maybe the near field element and the near field opportunity deserve some further discussion. But I would like to start this presentation, first of all, providing a very brief overview of the landscape of what we believe today should be the wireless future with all this 6G work and both in research and standardization. And then I will go to the main topic. The first part of this presentation will be focusing on the near-field communication and wavefront engineering and what are really the basics about it and what are the capabilities and promises. And the second part will be about exploiting these capabilities and promises in order to design the modules and the technologies that would provide this perceptive intelligence. And I think I will explain to you what I mean by that. So let me start with this introduction. I believe these are things that you know already. So the way that we see 6G is actually twofold, let's say. So on the one hand, there is the evolutionary path, and you can tell that this is more or less identified by these three usage scenarios that you see there in green: immersive communication, hyper-reliable and low latency, and massive communication, which are direct evolution of 5G usage scenarios. And the second part is what you see there in blue, which are the revolutionary path scenarios, including integrated sensing and communication, integrated AI, and ubiquitous connectivity. So already, I think these new scenarios tell you that we are facing a challenge of incorporating new performance metrics, new objectives that go far beyond what we're used to in communications. So these have to do with the monitoring, detection, tracking, localization, as goals beyond transmission of data, and also with performance requirements and metrics that have to do with reconfigurability, with resilience, tunability, you name it. So already I think the elements of sensing and the elements of intelligence, they are already there in the basic capabilities of these new scenarios. So that, I think, brings on the table a new challenge, which is about understanding, incorporating, and also satisfying new requirements that have to do with sensing and intelligence. But the important part of it is how these new elements, the sensing and intelligence, interact with communication. So are we looking at a challenge where communication will be leveraging sensing and intelligence? Is it that communication needs the sensing data and the AI to become better? Or is it maybe the other way around? Is communication going to serve sensing goals, to serve intelligence goals? So I think there is a very important, I think, thinking to do on that, because nowadays, I think this monolithic view of connectivity needs to change. And this is exactly this paradigm shift that I would call it that nowadays our new KPIs and our new KVIs are somehow, let me call them, bidirectional. So it is about being served by new opportunity, but also serving these new capabilities of sensing and intelligence. So what we've been doing for the last more than a couple of years is based on our work on MIMO, on RIS, on terahertz communications, we've been looking at a new system concept that incorporates this beyond communication metrics and goals and targets what we call sensing and understanding the world by mapping, tracking, imaging, and acquiring situational awareness. So this is the main topic of this project, Instinct, which is a European-funded project. And most of the work that I'm going to present today is actually part of the work of my team within this collaboration. The target usage scenarios, meaning the specification or the further detailing of the scenarios that we would like to consider, study, and serve, contain three important elements. The first one is mobility. So how can you deal with mobility in terms of not just transmitting data, but also localizing users and objects, tracking and management of the traffic? The second element is about monitoring and mapping the environment. And the third element is about understanding the new, if you want, a completely revolutionary aspect of connectivity, which is that of sensing not just the presence or the location, but also sensing the status, sensing, if you want, the micro movements, etc. So this is what, for example, augmented human sensing is about. So these are the three target scenarios in our work. And the system concept that synthesize these usage scenarios that we target contains these three pillars that you see on the picture. So let me just briefly explain those. So the first pillar we call sense to communicate. What it is that we use sensing data, we use sensing functionality to serve communication. The second pillar is communicate to sense. And this means that we're using communication links and technologies to actually provide and offer sensing functionalities. And the third pillar, we call it multifunctional integrated sensing and communication, which is the integration, the joint design of both communication and sensing that share common resources, common modules. That can be algorithms, waveforms, hardware, you name it. So the degree of integration, of course, depends on what you want to achieve, and also depends on the complexity that you're allowed to use and you can afford. But I think these pillars and targets, they need to be viewed not just as objectives for performance and new functionalities, but under the prism of today's availability of enablers. So the developments in that sense, they've been quite interesting, let me say. So large MIMO, extreme MIMO, reconfigurable intelligent surfaces, and all these large aperture, new, if you want, MIMO-like technologies have provided us with a lot of tools to be able to add tunability, flexibility, and also to address many of these new requirements that go beyond just the transmission of bits. On the other hand, the consideration of new spectrum, there's been a lot of work on terahertz and sub-terahertz for communications, and recently a lot of discussion about the use of FR3. So I think these two resources, spatial and frequency resources, can play an important role in motivating and also in allowing these new functionalities. So with that, I will go to the main part and explain how the work on large MIMO and the work on higher frequencies actually motivated the near field considerations. So as you go higher in frequencies and higher in number of elements, or what happens in a MIMO system, what happens is actually that you are talking about large aperture modules. Electrically large MIMO or RISs get you in this new situation where, as opposed to the past, many users can, in many scenarios that we described also, the scenarios of interest before, in many scenarios, many users find themselves in the near field. So until very recently, the near field was an area that was not really that much of an interest, mainly because it was not happening. I mean, the scenarios that we're studying were not in the near field. And on the other hand, like you see in the picture, these oscillations in the intensity that happen in the near field were not that, if you want, favorable, let me call them, for the techniques that we are used to design. But what happens now, this new situation where in the higher frequencies and in the large aperture arrays, we find ourselves in the near field. There is now a new opportunity to tune the local phase of the reflection coefficient and the array elements in order to tailor the beams, to go beyond the conventional beam forming and allow a new design principle, that of the wavefront engineering. So wavefront engineering provides this possibility to control the received power, density, and the beam trajectory. These new merits have to do not they're not just about the focus of energy, the energy efficiency and the control, but they can now be used for a dynamic management of the environment. For example, in terms of managing blockage, static or dynamic blockage, beam resilience, beam trajectory, localization, and tracking, most important, not just in the angular, but also in the radial domain. So first obvious use of forming beams in the near field is that of beam focusing. So you want to focus power to control the power density at a certain distance, and that you can do by using this new type of, instead of the linear, the parabolic phase. And the idea is that you have the opportunity to tune the aperture of the transmitter. For example, in the example here, what we do is that we illuminate an RIS. Yes, so by choosing, we can achieve at a certain distance. So you see there, for example, that as you increase this footprint, what you can achieve is you can achieve better focus, a smaller focal area with a larger power density. You can also use this right illumination in order, for example, to for different transmitter distances to again achieve the focus that you require in your beam focusing. And you see, as you would expect, that as you increase the distance of the access point that illuminates this RIS, what we achieve is a higher power density. Why is that? Because you increase the footprint that you illuminate on your RIS. Similarly, when you vary the angle with which you illuminate your RIS, again, you can change the focal area and density and power density. And in a similar way, you can actually vary the focal distance. So how far from the actual RIS is the distance of your focus area. So that tells us that we have the ability to tune beam focusing in order to achieve a desirable focal area with a desirable power density and size. And this size, as you can see here in the graphs, of course, they are naturally a function of the aperture. They're also the function of the distance, of the focal distance. And in that way, you can engineer the focal areas, especially useful functionality if you want to partition the area both in angle and in range. So this is already the beam focusing and the tuning of the focal area is a direct framework that provides you this opportunity of partitioning in the radial and the angular domain. On the other hand, you can use beam focusing as a way to do multiple, if you want, links, as a way to provide a new multiple access framework in the near field, because you can produce focal areas in different angles and distances, depending on, for example, the user that you want to reach with, for example, broadcast to selected multiple users. Now, going a step further beyond this parabolic phase and beam focus technique, one can actually achieve beams that have a desirable trajectory. So what we call accelerating or bending beams is this very idea. So the idea here is that you want your beam to follow a specific predefined convex trajectory, and you can engineer it to really achieve this. What are the purposes of doing that? You can see that in many ways from different perspectives. For example, you may want to make sure that your beam bends around an obstacle, or you want to achieve a certain avoidance of a certain obstacle, or you want to achieve interference-free regions. For example, you see here some, the chosen trajectories are parabolic and circular. So you want to partition the region in a interference-free region, and in that way implement an interference management strategy. Another reason for doing these bending beams is, for example, power transfer and energy efficiency control. So by using, for example, in this case, you see mirror symmetric bending beams, you can actually focus at a distance, leaving, like you see in the picture, a certain area that you can avoid. So, for example, say that there is a blocker just in front of you that you would like to avoid. And similarly to what we discussed before about beam focusing, you can in that way produce a multiplicity of bending beams. So in this new beam division multiple access scenario, the idea is that you have a number of selected trajectories that you want your beams to travel on. Of course, as you would expect, bending beams requires some resources to be able to materialize, and that has to do, of course, with the aperture. So you see here some numerical results that give you this idea of what it means, how the size of this footprint determines actually the maximum distance up to which the beam can propagate, and beyond which the beam will not anymore follow the selected trajectory. So the larger this aperture, the longer this distance can be. Overall, wavefront engineering by means of bending beams provides these new capabilities of interference management, blockage management, power transfer, multi-beam operation, and most importantly, what is, in my opinion, a very new idea is what we call near-field virtual routing. So to be able to follow a certain trajectory, a certain route at the physical layer, I think it is a very new idea. And once I was presenting these ideas, and some student asked me, so are we going to be able to see around the corner? So this virtual routing, I think, maybe not seeing around the corner, but I think the idea of virtual routing is exactly that we want to form beams that go around obstacles, for example. So the next step is to understand this situation of multiplicity of beams. Can we really use the beam design that we presented in order to provide this new near-field multiple access framework? What this means is that what is the equivalent of SDMA, for example, in this near-field situation? So we've been thinking and studying about this, and our goal was to introduce, first of all, to understand, and then to introduce orthogonality in the near field. So as you see, as is theoretically defined, orthogonality means actually that the correlation metric becomes zero. So how can we really design this type of beams? We want to make sure that the beams satisfy the correlation, but in order to be able to do that, you need a receiver that is actually able to capture the beam at a certain distance in order to satisfy this correlation condition, if you want. So we have designed cosine beams. These are special beams that are designed to be orthogonal and satisfy this condition. And we've actually shown that in terms of the spectral efficiency, like you see on the right, these are really optimal. The reason is that they can satisfy this condition, and as you can see, we show here the spectral efficiency for different numbers of users. They are really doing much better compared to the regular focused beams. I want to make a comment on this orthogonality of focal beams, but before that, I will just show you that based on this cosine beam design, we have also presented a systematic approach of selecting sets of orthogonal beams in order to be able to realize this, what we call near field SDMA, that offers this possibility for orthogonality in both the angular and the radial domain. So we believe that it is a very important feature to exploit in the near field. Maybe the most characteristic, the most important feature, the fact that you have visibility you can resolve in the radial domain. And this is also a very important thing if we consider localization. But just the comment I wanted to make is the following. When we think about orthogonality using focal beams, beam focusing, regular beam focusing, or specially designed beam focusing, we need, first of all, to understand that this requires a receiver with the right aperture. So as you go further in distance and your beam opens up, then you would need a larger aperture receiver in order to be able to capture it and then in that way materialize this orthogonality. That means that for certain distances, that becomes not practical anymore. So this is something to consider, to take into account when orthogonality is the objective. The second thing is that you may not even have this type of aperture. Maybe we're interested in the classical SDMA of single antenna receivers. So in that way, you cannot define orthogonality using this correlation metric. And orthogonality in that way means what it used to mean in the past in the single antenna receiver SDMA, which is that at a certain point, you have a maximum power in your desirable, and you have zero power in your undesirable links. So in that way, in a very similar way, it is still possible, although in the near field we have these oscillations that are complicating things, it is still possible to define a near field SDMA for single antenna receivers, making sure that you have the maximum power at a certain point using your single antenna, whereas everybody else is zeroed. So with that, I would like to just go now to the last part of this presentation. So how can we exploit these new capabilities? I think what we call perceptive intelligence, it is exactly this idea of designing functionalities using large aperture antenna arrays that are able to do wavefront engineering things that I explained before. So controlling the receive power density and focusing power in specific focal area of a certain size and shape, partitioning the angular and radial domain, providing self-healing and beam resilience, and bending beams along certain selected convex trajectories are the kinds of things that we would like to do, not only as a way to engineer the wireless environment, but also by doing, if you want, this reverse engineering approach as a way to detect, to read, to track, to sense the wireless environment. So an example of that is what we have been doing, and we were interested is, for example, blockage profiling exercises, how we can use beams to read the blockage situation around you. For example, you can collect statistical properties of this blockage, and in that way create the map of the wireless environment. A second example is to use a large aperture array as a sensor. So to use this capability of partitioning the angular and the radial domain in focal areas of selected sizes and shapes, and in that way be able to localize users. So what our algorithm is trying to do is, this is a two-phase hierarchical approach. The first phase is resolving in the angular domain, and the second phase is resolving in the radial domain. So this hierarchical approach is actually using, as you see here, increasing resolution. So the lower levels, they have larger angular and radial areas, and the higher levels, they go on and divide by 2. So the idea here is that when you reach the desirable resolution in the angular domain, then you use the beam focusing and the focal area in the radial domain in order to localize the user. So with that is not just for static situations. So one can use this algorithm in a tracking mode. So you can use the tracking mode, for example, using some kind of basic or even more elaborate prediction in order to be able to track a random motion. So as you understand, as you would expect, the usual trade-offs stand here. So what are those? This means that when you try to minimize the granularity of your tracking, obviously you can achieve better results in terms of accuracy, but robustness is the problem. So if you want to have a robust, then you may want to decrease the resolution, the granularity of your steps, for example. So there is always this situation where you want to hit the right balance between performance in terms of accuracy and robustness. What we've done actually in the framework of this Instinct project is that we also use some practical RIS designs that use only two-phase levels, just 1 bit, to show that it is still possible to do very acceptable things in terms of beam focusing. And you see here the results with the full phase, the 2-bit and the 1-bit. So that means that even in a practical systems with practical RISs, for example, these algorithms are really a possibility. And that brings me to the last example, which is a little bit outside the scope of Instinct, but we were kind of triggered, if you were motivated to check that. This is about physical air security. So, as you probably have heard, there is a lot of discussion about how terahertz communication may be a new opportunity for physical air security. In my view, near field may be the new opportunity for physical air security. For example, the tunability and control of power density, reconstruction of beams and self-healing, spatial orthogonality in the angular and radial domain, localization, environmental mapping and situational awareness may be new capabilities that can actually enhance and help physical air security, both because they are providing ways to read the environment and also because they are providing ways to write or maybe to engineer the environment. So this is like an example here that we measure the secrecy rate in two cases. In the one case, we're using beam forming, and in the second case, we're using beam focusing. We're in both cases in closer, in the near field. And you see how, as you would expect, because beam focusing is able to focus power in a restricted focal area, how actually secrecy rate is much, better in terms of the beam focusing. And we have many ideas and some plans to continue this work and actually create a framework or a system model where one can optimize secrecy rate by exploiting the new functionalities, the new possibilities of the near field. Here are some general, if you want, ideas that are around. RISs can be used for physical air security, or sensing of the presence is, of course, a way to avoid jammers, to be able to sense if and exclude if, and many other ways. And I believe that near-field processing and focusing has a role to play. So to summarize, let's see what we have on the table. What are the new elements? First of all, the use of large aperture antenna arrays. These being RISs, there are many names these days. There are LISs, large intelligent surfaces, large aperture antenna arrays, you name it. What is the idea here? There are two elements in it. The first is, of course, the large aperture, and the second is the tunability. So in that way, one can really exploit the fact that large apertures mean that the near field is now available to a certain larger distance, and you have the possibility to acquire this resolution capability in both the angular and the radial domains. You can focus, you can bend beams, you can use, you can partition in focal areas, etc. This, in combination with new frequency band, especially in the sub-terahertz regime, I think provides really an excellent framework. But of course, this is not alone. I think sensing, either as a communicate to sense or as a sense to communicate, is a very important element of that. And to provide further a tool for optimization, AI is, and machine learning is going to play an important role, especially in the cases when there is a large volume of data that we need to manage, or there are highly stochastic situations for which we don't have models. So I think this is a very important playground for machine learning and AI. The new, I think, differentiators of ubiquitous coverage, tunability, situational awareness, and intelligentization, these new key value indicators and the new performance goals, I think they will be nicely served by what the near field has to offer in terms of being able to control the power density, the receive power density, to control and manage blockage, interference, provide the beam resilience, also offer the possibility for the first time to create beams that follow a certain trajectory, for sensing and localization, for physical air security, like I explained, and for beam orthogonality. But I think at this point, I have to say that we need to remember this question. Is it really the situation where serving and intelligence, sensing and intelligence serves communication, or does it have to be the other way around? And which one needs more the other? So in our approach in instinct, we, of course, like I explained, we have the 3 pillars, and our idea is to follow an incremental way of materializing those. So our first step, if you want, is to take advantage of sensing capability and information for better communication. And then the next step is to use communication systems like MIMO, RISs, large aperture antenna arrays, to provide sensing capabilities. And the third step is to integrate these functionalities in a common design with common modules of the kinds of waveforms, of techniques, of transceiver designs, and resource management and network management module. But I think I would like to, as a concluding remarks, maybe mention a few things. Not that I want to be pessimistic or anything, but I think in this new phase where we are making this effort to really understand what it takes to materialize the goals and the visions for 6G, it is very important, it is critically important to properly consider and define the performance requirements and the metrics that we're going to use. I think this definition, along with the evaluation methodology, especially in this new situation where 3 out of the 6 usage scenarios, like I explained at the beginning, are completely new and contain elements that we have not been using before, like sensing, for example, and intelligence. It is critically important to identify the right test environments and to build evaluation platforms and analytical frameworks that would provide the possibility to really assess what it can be done. Of course, there is always the hope of availability of new resources, like, for example, new spectrum availability. But at the same time, I think one other important aspect is not just wait for new spectrum availability, but also to start considering new spectrum management approaches. And I would like just to give you a very small glimpse of what's happening in the ITU at the moment, where IMT-2030, which means 6G, is under definition and study, and all the preliminary studies have been completed. And we're now in this very important phase that I tried to explain before, of defining the performance requirement and the evaluation methodology with the associated test environment scenarios. I think this work, and I'm sure that there is a lot of research around it, and many research efforts contribute towards this direction, I think will be of paramount importance. So with that, I would like to maybe conclude and leave some time for questions. So thank you very much.